Okay, so we'll discuss mathematics in AI in this reading session. So we have linear algebra, maths about shapes, spaces, and how things stretch, move, or combine. Vectors and vector spaces. Vector align with direction, showing how far something goes. Vector addition, adding two directions to see whether they meet together. Then scalar multiplication, stretching or shrinking a line without changing its direction. Building blocks of shapes like Lego bricks, basis and dimension norms, measuring a line's length like using a ruler, inner product spaces, calculating angles or similarity like comparing two directions. So then we have matrices. Matrix, a grid of numbers to transform or organize information. Matrix operations, adding, multiplying, or flipping grids to solve problems. Diagonal matrix, a grid with values only on its straight line diagonal. Symmetric matrix, a grid that mirrors itself. Sparse matrix, a mostly empty grid. Determinants, a special number summarizing a grid's transformation power. Trace, adding up a grid's diagonal values like counting steps. So matrix decomposition, singular value decomposition (SVD), breaking grids into parts. Eigenvalues, eigenvectors, showing how grids stretch or shrink in special directions. LU decomposition, splitting a grid into two simple ones. QR decomposition, breaking grids into rotation and scaling steps. Then we have linear transformations. Linear transformation, moving shapes by stretching, shrinking, or flipping them. Projections, dropping points onto simpler spaces. Change of basis, switching to a new coordinate system. Special concepts: rank, how much information a grid holds. Nullity, how much of a grid is useless. Orthogonality, two things at perfect right angles. Orthonormal bases, perfectly neat directions, all at right angles and equal size. Pseudo inverse, a fix for grids that can't do their job perfectly. Tensor algebra, grids for multidimensional data. Calculus, math about how things change, grow or shrink. Differential calculus, derivatives, how steep something is. Partial derivatives, slopes in different directions at once. Gradient, a multidirectional slope guiding the steepest path uphill. Jacobian matrix, a slope map for multidimensional changes. Hessian matrix tracks how slopes curve. Chain rule, linking changes in steps. Linking changes in steps. Directional derivatives, slopes in specific directions, like tilting along a line. Integral calculus, integral adding up small pieces to find the big whole. Definite integral, finding finds exact areas or totals. Indefinite integral, a formula for totals. Multivariable integrals, adding areas in three dimensions. Vector calculus, divergence measures how things spread out. Curl measures how things twist. Stokes theorem connects twists and surfaces. Green's theorem links curves and areas. Optimization, gradient descent, a method to slide downhill and find the lowest spot. Convex optimization, finding the best answer in smooth bowl shaped problems. Non-convex optimization, solving bumpy problems with many low and high points. Lagrange multipliers, finding the best answer with extra rules. Constraint optimization, solving problems with limits. Now, probability and statistics, mathematics for understanding randomness, uncertainty, and making smart guesses. So, probability theory, random variables, numbers from chance. Discrete variables, random numbers that jump. continuous variables, random numbers that flow, distributions, patterns of randomness, joint probability, how two chances combine, marginal probability, a single chance after ignoring others, conditional probability, a chance that depends on something, Bayes theorem, updating your guesses with new information, expected value, the average outcome, variance, how spread out something is, like differences between difference between some similar things, how spread out something is, covariance, how two things change together, statistical methods, hypothesis testing, checking if an idea is true or just luck, confidence intervals, how sure you are about guesses, statistical significance, deciding if a result is real or random, maximum likelihood estimation, guessing the best explanation for data, expectation maximization is step by step way of guessing hidden patterns. So expectation maximization is step by step way of guessing hidden patterns. Bootstrap resampling, reusing data to check guesses, like retesting samples. Reusing data to check guesses, like retesting samples. So, stochastic processes, Markov chains, steps that depend only on where you are now. Hidden Markov models, HMMs, guessing hidden steps. Then Brownian motion, random wiggly movements. Information theory, entropy, a measure of surprise or randomness. Mutual information, how much two things share. KL divergence, comparing two randomness patterns. Comparing two randomness patterns. Cross entropy loss, a way to measure how wrong predictions are. Optimization, finding the best or fastest solution to a problem. Combinatorial optimization, integer programming, solving problems with whole numbers, like grouping people into teams. Dynamic programming, breaking problems into smaller ones. So then we have dynamic programming, breaking problems into smaller ones. Then graph based optimization, finding shortest paths. Heuristic optimization, simulated annealing, slowly searching for the best answer. Genetic algorithms, using evolution ideas to improve solutions. So, simulated annealing is slowly searching for the best answer. Then, genetic algorithms, using evolution ideas to improve solutions, like natural selection. And particle swarm optimization, teamwork of guesses to find the best solution. Teamwork of guesses to find the best solution. Discrete mathematics, math about step by step processes, connections, and logical thinking. Set theory, union combining groups, like set theory is union combining groups. Intersection, finding shared things, like overlapping groups. Cartesian products, pairing items from two groups. Logic, propositional logic, true false statements. Predicate logic, adding details to statements. First order logic, rules about objects and their relationships. Fuzzy logic, truths that's truth that's in between. Then graph theory, graph dots and lines showing connections. Trees, a special graph with no loops like family trees. Spanning trees, connecting everything with fewest lines. Shortest path, finding the quickest route. Centrality, measuring importance of the dots or the nodes. Combinatorics, permutations, all ways to arrange things. Combinations, choosing groups without order. Inclusion, exclusion, counting overlaps. Numerical methods, math for solving big problems with clever computer shortcuts and approximations. Root finding algorithms, Newton Raphson method, guessing solutions by following slopes, like finding zero on curves. Bisection method, splitting in half repeatedly to find where something crosses zero. Numerical linear algebra, iterative solver, step by step methods for solving grids. Conjugate gradient, a fast way to solve grid problems. Now, this GEMREST solve top grid problems by looking in the best direction. Now, numerical integration, trapezoidal rule, approximating curves using connected lines. Simpson's rule, approximating curves using smooth parabolas. Monte Carlo integration using random guesses to estimate areas. The Quadi using random guesses to estimate areas. Approximating curves using smooth parabolas, Simpson rule. Optimization algorithms, quasi Newton methods, faster ways to find best solutions. Niedermead method, finding lowest point without slopes. We'll continue in next lecture, next reading session.